Hi students, this is Dr. C. Shiva here. I welcome you to this class. Here we will actually understand the history of computing from the ancient days till date. What are all the updates are actually been happened in the computing? What is what actually defines a computer? We'll explore fundamental questions. What exactly is a computer? When was the first computer made? How did our computing needs evolve? We also consider how computers are becoming touchless and more portable, raising the question of simplification and future from factors. Computer, here I emphasize the difference between computer as a device and computing as a task. Computer as a device and computing as a task. Computers were not invented for entertainment or communication, but to solve serious numerical problems. In the 1940s and 50s, the term computing machine gradually evolved into electronic digital computer. Also, we'll see the definition of the modern computer here. A modern computer takes input, processes the information, stores it, and produce output. We challenge the assumption that physical peripherals like keyboards and monitors are essential. Modern systems can be voice controlled, gesture controlled, or embedded. Let's see one by one. This is the initial part of the computing, which is called abacus. Here we discuss the abacus, the earliest known calculating device dating back to 1100 BC. It worked using beads on the rods to perform basic arithmetic operations, and remarkably, it is still used in parts of Asia today. Even you can actually see the schools are actually now following these things. Analog calculators. This slide introduces Napier's logarithms and how they transformed complex multiplication into simplifier addition. Scientists quickly adopted logarithmic tables. The slide rule by Ortad and Schickard became essential tools in astronomy and engineering. Digital calculators and Pascaline. Now we transition to earlier mechanical calculators like Schickard calculating clock and Pascal's Pascaline. The first commercially produced adding machine. Pascal developed it to assist in tax calculations, marking the first business machine. So the first business computing machine is this one to calculate the tax, which is actually obtained by Pascal. Jacquard's loom and automation. This one. Jacquard loom and automation. Here we see early automation. Watkinson's mechanical devices simulated life, and Jacquard's loom introduced punch cards to control textile patterns. This idea of punched instructions later influenced in computer programming. You can see the year 1745. Charles Babbage, so the next person who had actually taken the computing into the next level. This slide highlights Babbage, the father of computing, and his difference engine and analytical engine. The analytical engine featured concepts like loops, branching, and memory, essential features of modern computers. Ada Lovelace and early logic. Ada Lovelace created the first program, making her the first programmer. So the known first programmer is a woman. So the slide also references the Gödel and Church, whose work established the limits of computability and influenced functional programming. So here you can see electromechanical computers. Now computing transitions from purely mechanical to electromechanical system, pure mechanical to the electromechanical systems, leading to devices such as uh, Hollerith's machines and Harvard Mark. Then is here in census calculation, Hollerith's census machine was actually being introduced. This explains how census data overwhelmed manual processing. Hollerith used punched cards and tabulation machines, reducing the processing time drastically and laying foundations for IBM. Then Harvard Mark in 1994, he had actually done several work. He built with IBM support. This machine used relays and mechanical components. It weighed 35 tons with 500 miles of wiring, showing how massive early computer were. Here you can see Grace Hopper and the first bug. Grace Hopper discovered a little moth inside a relay, coining the term bug. She worked on an novel ballistics calculations and influenced modern programming. So here, electronic digital computers, we now enter the era of true electronic digital computers from Atanasov to the Berry computer to modern systems. Yes, here. See, from slide 16 to 19, okay, these slides introduce Atanasov and Berry, who built the first electronic digital computer in 1939, applying binary mathematics and electronic switching. Is a person Berry, as you can see here, Atanasov Berry computer, which has actually been introduced with the binary mathematics and electronic switching. Then here you can see Colossus and Enigma based. Here you can actually see the cryptographic computing during World War II at uh, Park. See, we ask which technological milestone most enabled modern computing, either electricity, transistor, microchip, or storage. A transistor or microchip or data set. Okay, all these things. Okay, which are actually taking to the next level of the computing. Okay, so very important is actually the transistor. Okay, very important out of the listed things are actually the transistor. Okay, Shockley, Burdin, and Breton, they had actually invented the transistor, which is replacing vacuum tubes and enabling miniaturization, lower power consumption. For this work, they have actually been awarded with the Nobel Prize. From slide number 23 to 27. Okay, you can see here. So this is actually the ENIAC computer, electronic numerical integrated and computer, which is called ENIAC, electronic numerical integrator and computer. You can see the room-sized devices. Okay. So these slides are actually explaining the ENIAC's architecture and the programming complexity. They are actually following the Van Neumann's idea of stored programming architecture. Okay, stored program architecture. So this is ENIAC's wiring. You can see how the wiring used to be. Okay. Then again, the same technology being advanced here. Several browsers have been implemented with this. Okay, and you can see how the transistor is actually now they're sized. So one pen to the transistor can actually see how it is actually being sized. These are being created in terms of vacuum tube in the earlier model. Okay, so they used a Fortran also. Formula translation is actually the name for the Fortran. Okay, formula translation. Okay, it was designed to make the calculating the answers to scientific and mathematical problems to be easier. Exactly from the IBM. So very important topic here, integrated circuit. So which is actually 1958, in which the integrated circuits were actually being introduced. Computers used vacuum tubes earlier, bulky, fragile, and heat intensive. Intensives are actually very high there. Okay. So this is actually the first integrated chip circuits. So it is called to be the chip. For this, he has been actually awarded in 2000 for the physics. First commercial transistorized computer. You can see here. Okay. First commercialized transistorized computer. Transistor actually being implemented in the device and the computer. You can see how within the room it is actually being occupied. A computer is actually there is a monitor and small sized devices being associated with that. So these have been actually developed in 1960s. First high level programming language designed for scientific computation. So now here in 1962, a first computer game under word processor. Steve Russell at MIT had actually invented the SIVA, the first computer game running on a DAC PDP one device. So this actually look like a black, but it is actually a device. Okay, so it is all are actually small devices are actually being integrated. This actually the processor. Okay. Next, you can see in 1964, the mouse and the window concept are actually being introduced. And a wooden box, you can actually see a wheel, mechanical wheel, which can actually get a motion through the positions. It will be actually being detected from the mouse. So we can actually select the things. Okay, we can actually we worked directly using the interfaces like via the monitor we have actually given the input, okay, with the mouse. Intel dynamic memory chip being actually introduced in 1970. You can actually see here again in 1971 Intel had actually introduced a microprocessor. You can see how big size it is actually. In 1973 to 1976, Ethernet connections for networking from one to another, okay, where 3 MB per second can be actually achieved with the coaxial cable from one system to another system. Ethernet today can actually achieve several gigabytes per second. Personal computers are actually been introduced in 1974, 1975 in these years. You can see how it is actually the size of the computer, which is actually being developed by IBM. Okay, let's see the Apple will also be being listed in the coming slides. Let's see how it is actually. So IBM PC is actually again reduced in size and introduced a modified version. It will be released in 1981. So over the 20 years, you can actually see how drastically the digital world had actually changed the device size. So according to the Moore's law, device size will get reduced into half, right? So entire room size will get divided by two over a year. So very fastly happened. So Apple Macintosh in 1984 been introduced. You can see the design, which will also read the floppy disk, right? You can see the blue color devices being placed in the image in front of the keyboard, which is called floppy disk drive. Then the difference engine is actually been built in 1989 using Charles Babbage's original plans, 19th century manufacturing tolerances. The London History Museum built two functioning which replicas of the difference engine. Okay, see what is nano computing. Okay, we will see one few. Okay, so what is nano computing? Computing reaches nanoscale dimensions below the 100 nanometer. We call nano computing. Nano computing can enhance current technology and inspire new architectures. Nano transistors and quantum concepts, CNTs and silicon nanowires are explored over the years. CMOS uses doped semiconductors, but nanoscale behavior is always predictable. Then in gates and logic gates, logics are actually being introduced. Logic gates, then we call it as um, okay. So computing uses AND or XOR, not gates based binary states. But the future systems may require two logic gates to the new logic gates. Several logic gates will be actually using. So we need big logic gates in the future. Sorry, transistor inside the machine. Microprocessor rely on billions of transistors, but Moore's law slows after 2016 due to scaling limits. You can see the graph. Uh, there was actually a less number of devices from 1970 to 1996, even up to 2000. Then after that, okay, you can see so many dots. They are actually saying that several devices are actually being introduced at the time, but it actually is getting slowed down while moving towards to the 2025 from 2016. So there are several obstacles are actually there in the modern computing: heat dissipation and electron charge limitations, which leads us toward nanotechnology um, and beyond the technology. Okay, we need to actually go for a SET and quantum tunneling concept. A single electron transistor demonstrate quantum tunneling when structures become extremely small. Okay, so why we go for that? Okay, before that we'll understand the old model where the devices are actually getting like a heat and they need to actually get small down. Okay, so in order to avoid that, where we go for even lesser with so much amount of control over the engineering. This says about single electron transistor concept. You can see uh, titanium dioxide is actually the barrier island. You can actually see the barrier source drain. How the barrier drain sources are actually being mapped. So it is on a surface. It is being created and been reported in 1996. This is actually the model for the single electron transistor, which is made by the scanning tunneling microscope by means of oxidizing on the titanium surface. The surface are actually being oxidized into titanium dioxide. It is very identical to the devices are actually being realized in terms of silicon transistors. Silicon will be actually being oxidized into silicon dioxide. They are extremely small. Single electron transistors are actually very extremely small. Uh, they are actually going like quantum tunneling concepts beyond the classical transistors. Future nanocomputers may use quantum dots and cell-based architectures. Early systems may be nanometer scale classical computers, while future algorithms offer great power.